If you have a small spherical object that is oscillating so that its radius changes periodically with time, it produces a spherical sound wave that moves outward from the source at constant speed. So here's our little object. It's vibrating back and forth symmetrically in all directions. It will create sound waves that go radially outward from it. And these radially outgoing sound waves, when they reach some distance r, are spread evenly over the surface of a sphere of radius r. And maybe you remember from geometry class that the surface area of a sphere is 4 pi r squared. So that means that the intensity of sound waves at distance r away from the source is the power of that sound source divided by the area, or surface area of a sphere, 4 pi r squared. This is generally true for spherical waves. Not all waves are spherical, but many sound sources act like this. Some sound sources are more directional, like a loudspeaker tends to be kind of directional and projects the sound more or less in a cone. Human voice is somewhat directional too. When I talk, most of my sound goes forward, but some of it goes behind me as well. So this is kind of an idealized scenario of being spherically symmetrical, but it's pretty useful and surprisingly general. This idea of some quantity being evenly distributed over a spherical surface turns out to be useful in gravitation, in understanding electricity and magnetism. It's because there are many phenomena in nature that follow this 1 over r squared thing. 1 over r squared dependence is known as the inverse square law. And it's a consequence of the fact that we live in a 3-dimensional space. When you have a source of something, and that something propagates symmetrically outward, it's spread out over a sphere whose surface area is 4 pi r squared. So anytime you have something emanating from a source, whether it's gravity or the electric field or sound waves or light waves, that's going to obey an inverse square law. It's because we live in 3D space. Okay, so let's do an example problem where we use that surface area to calculate some stuff. This is example 14.3. So you can hear me talking right now because some of the sound is coming out through the back of my head. Also, some of the sound is reflecting off the wall, but I am shooting some sound behind me as I talk. Okay, in this example we have a small source that has a power output of 80 watts. By the way, if you have a stereo, it will tell you the power output of that stereo if you ever want to do some of these calculations at home or in your car. 80 watts that'd be pretty common for a stereo to be about 80 watts. So let's find the intensity 3 meters from the source. To do that, we just plug into our intensity definition. And use 4 pi r squared for the area. Now, maybe a more interesting question would be, at what distance would the intensity be 1/4 as much as it is at 3 meters? And you can do this the hard way or the easy way. So the hard way would be taking this intensity, dividing it by 4, and then solving this equation for R. The easier way is to recognize that this intensity goes like 1 over R squared. If you double the radius, you get 1 over 2r squared. And doing the algebra in your head, that would give you 1/4 the intensity. Doubling the distance decreases the intensity by 1/4. That's just what happens when you have an inverse square relationship. If you tripled the distance, your intensity would be decreased by 1 over 3 squared, or 1/9. If you made the distance 4 times as long, the intensity would be reduced by 1 over 4 squared, or 1/16. If you made the distance 5 times as long, it would go down by a factor of 25. Okay, so what distance is the intensity 1/4 as much? Well, it's when the distance is twice as big. So it would be at 6 meters. And part C, find the distance at which the sound intensity level is 40 decibels. Again, I hate this term intensity level. It's so confusing because it sounds just like intensity, but it's a completely different quantity. So I usually say decibel level instead. I don't like that term, but that's how the problem wrote it. All right, well, we use our definition of decibel level, 10 log I over I naught. And we need to solve for I and then replace I with this stuff and ultimately solve for R. So it's a bunch of algebra that goes on here. let's do it. Let's see, 40 decibels. Okay, so we get 40. By the way, decibels is not actually a unit. It's like radians in that sense. It's reminding you that you're talking about a certain situation, but decibels aren't units in the same way that meters or kilograms are units. So when you put 40 into the left side of the equation, there's no units here. Both sides of this equation are dimensionless. All right, let's keep going with this algebra. I divided both sides by 10. Now I need to undo the log. So I go 10 to the 4. I raise both sides to the 10 power. So I equals 10 to the 4 I naught. I naught is 10 to the minus 12, so that is 10 to the minus 8 watts per square meter. So we have a value for I, and now let's use our definition. I equals P over 4 pi r squared. We want to solve for r. So r is P over 4 pi I square root, and we have values for those things now because the power was 80 watts and the intensity is 10 to the minus 8 watts per square meter. And after all that algebra, we find the distance. 2.52 times 10 to the 4 meters. So you got to get kind of far away from that 80 watt sound source to reach a 40 decibel level, which is a little bit quieter than normal talking. It's a pretty faint sound. All right, that's it for this video.